Hello. So, this is an interesting thing that I've been thinking about for a while, and I finally spent a little time digging into it a little bit more. And the real question is, when you're building a rocket, should you build a tall and thin one, or should you build a short and fat one? So, that's what we're going to be talking about. Now, this measurement is expressed using something called the fineness ratio. And so say we have a rocket, 14.5 meters tall, 1.3 meters around. Take those two numbers, divide them, and we get 11.2. And that's just a measurement of the fineness ratio. Now, it's not perfect. It might change if you have different payloads, different payload fairings, or all those sort of things. But it's basically a pretty standard way of comparing tall and thin versus short and fat. Now, there are a number of trade-offs that might come up, and this is a short list. It's not intended to be an exhaustive list. Short and fat on this side, tall and thin on that side. And what do we see? Well, short and thick rockets are less bendy, and they are also stronger. So those two things go together. So you think if you had a piece of wood this shape, short and fat, it would be pretty hard to break. It would be pretty strong. If you had a piece of wood that was tall and thin, it would be a lot easier to break. Shorter rockets have less drag. The amount of drag you get is mostly proportional to the frontal area of the rocket. So the rocket on the right has much less frontal area, much less drag. The one on the left has more room for engines. So all the engines you want to fit underneath your rocket, they have to have room to fit. And if you've looked at a Falcon 9, for example, you know that those engines are packaged very, very tightly. So a thicker rocket gives you more room to put your engines. A thin rocket, tall thin rocket, is much easier to transport. And in fact, the SpaceX Falcon 9, its diameter is set specifically so that it can be transported by road across the US. So it starts in Hawthorne, California, then it gets shipped by road to McGregor, Texas, where they test all the stages. And then it either gets shipped back to California to be launched at Vandenberg Air Force Base, or it gets shipped to Florida to be launched from one of SpaceX sites there. So if you can't do it on road, you might be able to do something by rail. Rail can be tough too because of the bend. It pretty much means if it's too big for road, you're going to be shipping it by ship or barge. And that's slower, more expensive, so tall and thin is a little easier to transport. This might be an obvious one. The short and thick rocket needs a shorter launch tower. You don't have to build a really, really tall launch tower. And then finally, there may be something, depending on how you build it, from a factory perspective. If you had a rocket that had a really big diameter, it might not fit in your factory if you were building the stages sideways. And that's how most rocket stages are built. So you just might not physically be able to fit it. You might have to build a new factory. There's one more trade-off, and that is a weight trade-off. And I'm going to kind of go into depth on that one. But before we do that, let's look at a bunch of rockets. So these won't be exact, but these will give you a basic idea of how rocket fineness varies. So Falcon 9, kind of the benchmark for a tall and thin rocket, and it has a fineness of about 18. Depends upon whether it has Dragon or a fairing on top of it, but that's pretty close. You notice Soyuz, Atlas V, Electron, and Starship are all pretty high in terms of fineness. And then if we get way down at the bottom, the three bottom, Energia, which is the Russian previous big launcher, And I put Saturn V, the two-stage variant, up here because Saturn V is really a two-stage orbital rocket. The third stage was really mostly about getting to the moon. And then finally, just because I thought people might care, I put New Shepard on there. New Shepard's obviously only a single stage, but it's a very short and fat rocket, as rockets go. So, the ones I showed you earlier, obviously the Falcon 9 on the left, and the Energia on the right, and you can see they look very, very different in terms of, tall and thin, short and fat. So, one of the things I thought was interesting, and this is really what led me to investigate this, is whether the tank design really has a big effect on this. And if you look on the left, we see compressed gas cylinders, and you can see they are mostly tall and thin. And as you get bigger, they get taller and thinner. And on the right, we see chemical plant or petroleum storage, and we notice those tanks are really big, really wide, and not very tall. So what would we want for a rocket? Well, okay, so as usual, for my talks, there's going to be some math ahead. Don't worry about the specifics. I provide the specifics because I think some people will want to know, but I will tell you the parts that are important. So what I'm looking at is rocket tanks, and rocket tanks have a very specific structure. At least most of them do. What we care about is the surface area of the tank, because we have the surface area. Most rockets are a given thickness, although this is not universally true, but they're a given thickness. If you know the surface area, you know the amount of material, and you can figure out how much it weighs based on the material. And this is going to be an approximation because, as I said, different rockets use different approaches, and they use different approaches in different areas of the rocket. And then the other thing we care about is the volume. So the amount that the tank will hold. So if we have a high surface area and a low volume, that'll be a heavy tank. And if we have a low surface area and a higher volume, that will be a light tank. And we want a light tank. So how can we calculate this? So I'm going to start with the main body of the rocket. So the main body of a rocket is a cylinder. It's an open cylinder. It has a height h and a radius r. Now I chose radius rather than diameter because it makes the math easier to understand, although most rockets are described in diameter rather than radius. So we can go and do a little math, look this up. The area of this is pi 2r times h. And that's pretty simple to figure out. If you cut the cylinder and rolled it out, you would see that the perimeter of the circle is pi 2r, and then h is the height. So that's pretty simple. The volume is also something you can look up. It's pi r squared h. So that's for the main body. Obviously, that's an empty cylinder. That doesn't really help us. We need to have a dome at the bottom. And the dome, well, the dome is really just half of a sphere. So both the area and the volume are going to be half a sphere. So the area, 2 pi r squared, and the volume, 2/3 pi r cubed. Now, in addition to the dome at the bottom, we need a dome at the top. And then we typically have, for most tanks, we have a dome in the middle. Now, there are some designs where you essentially have two separate tanks, and so you'd have two domes in the middle. I'm going to assume we just care about versions where we have this shared dome in the middle. So, do a bunch of math. We see the total area is the area of the main body, pi 2r h, and then there are 3 domes. So there's the top dome, the middle dome, and the bottom dome. So 3 times the area of the dome, so 3 times 2 times pi r squared. The volume is pi r squared h, the main part, and then 2 times the volume of the dome, because the top and the bottom dome add volume, the middle dome does not. Do some simplification. Area pi 2rh plus 6 pi r squared. Volume pi r squared h plus 4/3 pi r cubed. And this is something you don't need to know the details. I just thought it would be interesting to derive this. So now I want to go and look at what this really means from a specific design. And I'm going to start, essentially what I did is I said, if you know the volume that you want to store, and you know the radius that you've chosen, you can figure out how tall the tank is, at least how tall the main body part needs to be. So what I'm going to do is, for a given diameter, we've chose the radius for that diameter. We can calculate h. We can figure out how much metal is required, and we can figure out the weight. And we can plot this for different diameters. So essentially we're saying we know the volume. Let's see what happens with different diameters. And when you do that, I built a little model in Excel that would do this. You end up with a chart like this. And you can see at the low end, a small diameter, you end up with kind of an extra, a heavier tank. And that's because you have a tall, thin rocket. So you're putting more material into the tank. And then on the right side, if you get your diameter gets too big, you end up with also a heavier rocket. Now, for these mass measurements, I'm not taking into account the fact that a tall, thin rocket likely needs to use heavier material than a short, fat one, simply because it's taller and thinner and more bendy. So this is just assuming you have the same thickness. So let's look at some real examples. So Falcon 9 booster, I went and dug up some numbers. We know how much propellant it is. We can use the mixture ratio that we know for the Merlin engine and figure out how much volume that is. I'm not going to do the calculations here, but if you want to go and look at my video on first stage boosters, you can find the calculations there. Here's what we get for the F9 booster. And draw a little line here. We can see 3.7 meters is the diameter of the booster. So that would be about 5.2 tons of mass. Making some assumptions as to the construction and the material. If we could push it up to 7 meters, it would be 3.9 tons, and that would save about 1.3 tons of mass. So if you bumped Falcon, you essentially doubled the diameter of Falcon 9, it would be a little bit lighter, about 5% lighter. Now, 5% lighter sounds like a really big deal, but generally speaking, you could expect that you maybe get 1/6 of that would show up as payload. Generally, if you take 6 kilograms off of a booster, you get roughly 1 kilogram off of added to payload for the second stage. And speaking of the second stage, so we know the propellant, we can calculate the volume, and here is the chart we get for the second stage. So 1.68 tons at the current thing, and 1.64 tons if you kind of moved to the best part, or the best diameter. And that's a difference of 0.04 tons, or about 40 kilograms. That really doesn't seem like a lot. It's only about 2%. And I thought about this and was kind of surprised, because I've heard that, Falcon 9 is smaller than the diameter they would want. But basically, this is really just a matter of them choosing propellant based upon propellant capacity based upon the tank size that gives them what they want. So I think you've you know what the diameter is, and then we want to build a second stage that is very light, and we end up with one that's pretty close to optimal. And remember, that's pretty close to optimal under my model, which has some really obvious issues to it. So I think for this one, we can say that, hey, that looks pretty close to what you would expect. The other obvious one is Super Heavy and Starship. Since Super Heavy and Starship, they weren't constrained by shipping, so presumably they could have chosen a more realistic diameter or a more optimal diameter. So Super Heavy, lots of propellant, lots of volume. Here's the chart for Super Heavy. And what do we see? Well, we see 9 meters, about 65 tons. 14.5 meters, which would be a very big rocket, is about 53.7 tons. So 11 tons difference, which really seems like a lot. Wow, that's a lot. But it's only about 6% lighter, which means the effect on final payload for Starship would probably only be a couple tons. And since the hope is that Starship will have a payload of 100 tons, it really doesn't look like that big of effect. But I kind of expected this one to be closer than we ended up with. Starship, do you have any predictions? Anybody? Okay. Propellant. Here's what we get for Starship. Okay, at 9 meters, 27.3 tons. At 10 meters, 26.8 tons. So only about 500 kilograms difference. And I think basically what we're seeing is pretty much the same thing that we saw with Falcon 9. And it's pretty clear, I think, in both cases, from this and from some other things that I've looked at, that the way SpaceX approaches things is they design their second stage first, and they make sure that it has the capabilities they want, and then they design a first stage that will get the second stage where it needs to be. So here we see the second stage is pretty much optimal, at least within the limits of my model. So this was really not the result I expected. I expected that Falcon 9 would look much, much less optimal, and that Starship would look much better. And from this perspective, it doesn't. Now, obviously, I said earlier that Falcon 9 may need thicker walls than it would if it was thinner. And if you had a model with that, it probably looks less optimal. So, really not a big difference, and probably easily within the margin of error in my model. So what else could we look at? Well, I thought the Saturn V might be an interesting choice because it's not all the same diameter. So here's the first stage of the Saturn, the S1C. I couldn't find a nice upright picture of it, so I took this transport picture and rotated it so that it's upright. That's a big stage. Here's the plot, which you might recognize as the first plot I showed. So the Saturn V S1C stage is 10 meters in size. Oh, and I'm not going to show you the other calculations here. What you can see is that's pretty close to optimal, or what we would expect. And we would kind of expect that Saturn V had a lot of engineering going into it, and they would have chosen a fairly optimal fineness. Second stage. The S2, here's a nice vertical one. It's being assembled in the vertical assembly building. And what do we see here? Well, S2 is also 10 meters, and look where that lines up on this chart. And wow, isn't that interesting? It's almost exactly where the minimum weight is. And that's the kind of thing you see on upper stages. It's what we saw on both Falcon 9 second stage and Starship. And here it looks pretty good. Now, do you have any prediction of what we might see for the third stage? Well, third stage, here's a picture of the third stage, and here is the graph. And the third stage is smaller. Its diameter is 6.6 meters. Once again, pretty much at the optimal location for a stage this size. So the fact that I got reasonable numbers for Falcon 9 and Starship second stage and very good numbers across all of Apollo leads me to believe that my model is actually somewhat decent. Now, since we're talking about the third stage, I need to ask a trivia question. You notice the third stage is S4B. And the trivia question is, why is it S4? And I guess, what does the B mean? Where's the the S3 stage? We had S1, S1C, then we had S2, and now we have S4B. And the answer to that is that Saturn was really conceived as a family of rockets. And when they were doing the design, they didn't know how big the rocket would need to be, and they thought that they might actually need more stages. So S4 was the stage designed for either a 4 or 5 stage version of Saturn. So that was the way it was defined up front, and when they finally decided to build the Saturn V, they thought it would be confusing to rename the S4 stage to S3. So the Saturn V variant ended up being S4 and B because it's a modified one. So what's the summary? Interestingly, stage diameter was actually less impactful than I expected. I thought that choosing one of these diameters or one of these, either big fineness or small fineness would have a big effect. And the second thing, well, second stages are more optimized than first stages. And I guess that's really no surprise because second stages are always more optimized than first stages. Just inherent in the physics and what you're trying to do. So I hope you found this kind of interesting. If you like this sort of stuff, please subscribe. And thanks.